Uh, Relatively quick day for us today. We're gonna do some couple named problems. We're gonna do what we call our ice skaters problem, and then our running into a wall problem, which is kind of the reason for the video here. I think Doug was okay in this one, but it still is pretty darn funny, right? Chasing stuff and going. All right. In homework 4-2, skip number 3 and number 10 for me. Okay. They're nice problems, but in the grand scheme of life for us, we don't need to necessarily worry about those too much today. Okay. All right, here we go. So we're starting with the conservation of momentum, basically a change in momentum problem or impulse problem. All right. So here's your ice skaters problem. Um, Robbie, 80 kilograms, Roberto, 50 kilograms, are on a frictionless ice skates facing each other completely at rest. Roberto pushes Robbie with a force of 50 newtons for zero point 0.5 seconds, which sends Robbie gliding across the ice. How fast is Robbie moving after the push? How fast is Roberto moving after the push? All right. So when we look at this, is what we're basically seeing is we're seeing two people facing each other, going to push apart. All right. So um, there's our first bit of information. We've got a force of that Roberto exerts over a time period. We know the mass of Robbie. We know the mass of Roberta. We want to find the velocity of Robbie first. Now, here's the thing. In order to find the velocity, we either need a distance, we need an acceleration, we need a time. Well, all we have is time. Well, that doesn't help us. So then what we have to do is we have to look at our change in momentum or conservation of momentum formulas. All right. So the only equation that's going to have speed is our change in momentum or our impulse, m delta v. All right. The thing is that we don't have the impulse yet, but we can find impulse by doing the change in impulse is the force times the change in time. So what we're able to say is our change in momentum is going to be 50 newtons times half a second, right? That's a nice thing about them giving us a force and a time together. That tells us what that change in momentum is going to be, all right? So using that, we can find that our change in momentum is 25 newton seconds, all right? Once we know a change in momentum, now what we can do is we can find out how fast Robbie's moving, all right? So remember, these two things here, let me grab a pen, all right? This Newton second and this kilogram meter per second, those are both the labels for change in momentum or impulse, all right? So what we see is then 25 equals his 80 kilograms times delta V, all right? So his change in velocity from starting at 0 is going to be 0.3125 meters per second, all right? Now, likely in the test, likely in a quiz, we're going to ask you for that change in impulse or that change in momentum, that impulse first, all right? Just so that you're aware, that'll probably be the first one. Hey, what's the impulse here? And then this will probably become a B answer. How fast is Robbie moving after the push? Okay. Now, once we know the impulse, this is going to be the same for Roberta, right? So when we look at this whole entire thing here, what we're going to see is that Roberta experiences the same change in momentum that Robbie does. So hers will be also 25 newton seconds or 25 kilogram meter per second. Okay. Now, with her different mass, that's going to mean that her velocity is a little bit more. She's lighter, she's going to go faster. He's heavier, he's going to go slower based on that same momentum, right? So, with an ice skater's problem like this, what you're really going to see is that these two people are going opposite directions, right? We're able to find a force between them and then use that concept to find impulse. Once we have impulse, then we just work with impulse to find either a mass or a velocity based on that force and time that was given to us. All right? So that's an ice skater's problem. All right, next one. Running into a wall. Okay, this one's kind of weird. So, a human is running along with his or her eyes closed at a pretty good speed, 7 meters per second, when they run right into a wall. Since they don't catch themselves at all, they slow down to a stop in the distance that the body can deform, roughly 5 centimeters, 0.05 meters, which means that they come to a stop in 0.014 seconds. Assuming the human's mass is 75 kilograms, determine the average force they experience when they hit this wall. All right, so now what we want to do is we want to find force again. Well, if we had an acceleration, we could do that, right? So there is some school of thought that you could use the average acceleration formula there. I don't want to, all right? I want to do this through impulse, okay? The reason that I want to do it through impulse is because I know here that, again, that my impulse is mass times the change in velocity. It's the easiest way to find it, in my opinion, all right? So what we see is our change in momentum is going to be the mass times that change in velocity. So we take our 75 kilograms and times it by a -7, right? So in this case, our change in momentum is going to be -525 kilogram meters per second, all right? So now that we know the change in momentum, or that impulse that happens there while this person is decelerating for us, what we're able to do is say, all right, that is still -525. And it's either, sorry, this is supposed to be kilograms. Let me fix that here for you. Ooh, that's bad, G. Sorry about that. That's going to be kilogram meters per second, or -5, is it 525 or 524? 525. God, Lord, folks. I can't do these late at night anymore. This is supposed to be a 5. All right. So 525 Newton seconds. So now that we know that that's our impulse, what we're able to say is the time it took for this thing to stop was 0.014 seconds. So -525 equals F times 0.014 seconds. Again, solve for F by dividing over the 0.014. And what we see is that's going to be -37,500. So if we're going 16 miles an hour and we slow that fast, that's basically 8,431 pounds of pressure putting on us. Okay. Negative, positive, doesn't matter to me. All right. I just want the 37,500. So if you're worried about, oh, Mr. Schmelze, I did this a different way and I got a different number and I got a positive instead of a negative, hey, we're super good there. All right. So again, that's running into a wall. So in this case, the difference between this one and the previous one is that they gave us a mass and they gave us a velocity. Because they gave us those two, we can find impulse. Once we know impulse, then we can go find the force. So all we're doing is just working that delta P, M delta V, delta P, F delta T. So we're just working those two equations, basically these bottom two ones right here. Okay, don't know if you can see those or not, but those are the ones that we're working through right there. Okay. Section 2, Section 3 really start to hammer on this stuff. Tomorrow I'll talk you through impulse of a rocket, and also maybe throw some more ice skater problems at you, running into a wall problem and stuff like that for you too as well. Okay. So today the goal is, now that you're done with lecture, hop into those homework questions and really start to see those and see how those work out for you. Okay. Don't forget to skip number 3 and number 10 on homework section 2. Okay. Otherwise, folks, have a phenomenal day and we'll talk to you soon.